All right, let's get rolling. I probably will finish up maybe like 2 or 3 minutes early today. I have a virtual visitor on Zoom, so I just need commute time back to my office. And there's about a 70% chance they won't show up, is how the virtual visitors typically work, but we'll deal with that. Okay. So if I remember correctly, last time we were walking through our character read device, and we mostly went through the code, but didn't quite, like, I showed you proof that it was running, but we didn't quite go through the process of running it and stuff like that. Okay, I'm going to show you a couple other things related to that today as well. So let me bounce back over here. Okay, so let's just quickly review this real quick, just so we have our minds back to where we were from last time. We talked about the prototype functions last time for 1-pass compilers versus 2-pass compilers more modernly, where the newer solution for this is header files, right? So that's what all these are. These just say, here's some functions we will be writing. Here's some macros of stuff that we will be, like, kind of, these are like constant variables. We're going to be naming our device chardev. It's going to get a major number that will be assigned to it. Here's the message that we're going to read in. This is our file, or this is our simplified file operations struct that GNU gives us. So instead of those 4,000 things, here's read, write, open, release. Give me information about these guys, and we can probably roll with that for most character devices. All right, here's our init module and cleanup module, the same things we had before. So when we initialize this module, we're going to see this here in a few minutes. We register that character device. So this is a function that already exists. And this is the guy that magically, so we're saying, I want to register a character device. Here's the device name. Here's the file operations. This guy will return for me some number, kind of the unique ID. Although it's not that unique. I think once it sets it once, it's kind of like a DHCP server, where as long as once you connected to it once, it pretty much keeps handing you the same IP address. Kind of interesting. I've been getting the same major number. This always gives me the same number for this particular code. I'm sure we'll get a different one for a different module, but whatever. The idea is that we ask for a unique identifier from Linux. It hands me a unique identifier. And as long as that unique identifier is 0 or greater, it must be real, right? Otherwise, you scream, bad things happened. Okay, this is just stuff that's going to get print out to that D message, and we'll look at that here in just a few minutes after I go through some of the script files that I created to make life a little easier, because we do have lots of little commands that we have to keep typing in for different stuff. So one of the nice things you can do with Linux is you can throw these things inside of a script and then just call the script. So we'll just look at that for a minute as well. But in any case, this is what gets dumped out to that log file. But more importantly, it tells you, hey, you can go ahead and run this command right here, and it'll fill in the major number and the device name. So it'll be /dev/chardev, and then whatever the device number is, which is like, I think it's like 227 or something like that on here. So whatever it read in as that major number. So it creates this screen. And what it allows you to do is you copy this and you make a node inside of /dev that links to this actual device. So we create a file, and so make node creates a special kind of file that we put inside of /dev, and it links it to this major character device that was assigned. All right, so this is actually an extra command that we have to issue after we've installed the module. We'll go through that process here in a few minutes. Okay. This is what happens when we clean up the module, we unregister the device. Realistically, externally, we should also remove that node file. And I also put that in a script. So like I said, we'll walk through those. This is what happens when we open the device. Remember, there's two steps. We open a device and we read from the device. Right now, our write we haven't implemented. So opening a device, we have this static variable counter. What does it mean for it to be static? We talked about this at the beginning of class last time. Go ahead. Okay, it's scoped to the program in this case, since we're dealing with C, not C++, because there aren't classes. And when we say it's scoped to the program, effectively, what does that mean about this variable counter? Go ahead. Okay, so it persists beyond this call of the program, right? So if I call device open 5 times, counter will start off at 0, but then its value will persist as we make changes to it. Okay. So we count the number of times the device has been opened. We print out, I already told you some number of times, hello world, and we have our counter, and then we increment counter. So this variable right here, even though we're defining it here and we're initializing it and at the beginning to 0, because it's static, it will stay alive and continue to allow us to count up to 1, to 2, to 3, to 4. Okay, and as he pointed out, if you want to apply your Java knowledge to this, it's like it's part of those singletons we used to create, where you have one class that had a bunch of static stuff in it, and we can change those variables and just kind of stayed, they just lived. This is the same thing, except it predates object-oriented coding, so it belongs to the program instead of the class. All right. So this is us incrementing that counter so that the next time you open the file, it'll say, hey, I already told you another time and another time and another time, so on and so forth. All right. This is a function called try module get, where you pass in the module. So this is what actually triggers the read. This is what happens when we release the device. So this will decrement the usage count, because keep in mind, once you have a device, in this case, a character device, you might have multiple people all trying to read from it at the same time. So just because I read from it twice does not necessarily mean that somebody else didn't read from it 5 times or something like that. All right, so when we try to release this module, and we call module put, which is also built into the module library, it's going to only get rid of the module when the usage count gets down to 0, the number of people who are currently talking to it. So it's a shared resource. Here's the thing we actually wrote here, the device read. So this is, hey, if I'm going to read from the device, what happens? We're going to read in some number of bytes, and we'll put that out to the user, which ultimately for us goes to the screen. And then so this actually puts it out to the user. This is the pointer to that message. And notice the link here between device read and device open. Device open prints to a string this message. So we have this variable called message, MSG. And notice message belongs to this program. It's all the way at the very top, well, close to the very top. We have a static character pointer called message pointer and a static char called message. So they belong to the program. They're globally available. What we're doing when we open is we are writing, so sprintf prints to a string, whereas printf prints to the screen. All right, so we're printing to a string. What string? Message. This is what we're printing. It's a formatted string, just like printf. Then we're incrementing our counter. Then we're updating this pointer to point to the message we just printed to. And effectively, what does printf do? Printf is going to write this whole string, and then ultimately terminate it with that \0 string termination character. So potentially, if you had written like a a gigantic 5,000 characters previously, although I think we only built it to hold 1,000 maybe. I don't remember what the number was up there. But let's say we put a lot of stuff in there, and then the next time we wrote something shorter, we didn't erase that end stuff. All we did is we moved for our \0 where the string termination character ended up being. So if you chose to use memory math to walk past the end of your \0 thing, you'd start running into characters from the past. All right. So what we're doing here is we print to a string, and then we're setting that global message pointer. So it's like a global. It's global here, but it's also global to as long as this program keeps running by being static. All right. Then we trigger module get, which does the read. And the read utilizes this variable message pointer. So go down to read. Notice here we're asking some questions about the value of message pointer. Then we're saying, while the length has something in it and message pointer is a thing, go ahead and put to the user, this is a single value. That's one char we're putting to the user. Okay. The star says, give me the value at an address, right? Message pointer holds a memory address. This will be, and a message pointer is a char pointer. So this will boil down to the character that lives at this memory address. Okay, and we're going to put this into this buffer that's related to the user. Okay, so it kind of builds up a string and then dumps it to the user. Then we increment our message pointer. So what used to be the character at the beginning address, now the address is one forward, then one forward, then one forward. So message pointer, when we first got in here, pointed to the very beginning of the string. And then rather than keep track, I'm not sure why they actually changed the pointer as opposed to just creating an integer that counted from 0 to 1 to 2 to 3 and let that be message pointer plus 4, get you bucket 4. Message pointer plus 5, get you bucket 5. But whatever. All right, then we're decrementing length. So length started off as the total number of characters in there, and then we're decrementing it towards 0. And we're incrementing the bytes read. These are the bytes ultimately delivered to the user. All right, so that's how open and read work. Write, we didn't implement. All right, make sense what this program's trying to do? All right, so let's go and look at the cadence for installing a character device. Right here. So installing a character device, we insmod, let's just say install the module. Install the module, add the special node, as far as we're concerned right now, to /dev, whatever the name of it is. We're going to be looking at an alternative to this next, which deals with the Proc file system. All right, so install the module, add the special node to /dev. Now we can read/write whatever you've implemented for this. From that /dev/whatever. Just say based on what was actually implemented. Note that reading or writing requires the file to open. So we're still always going to call open on that file. And then the next step will either be to read from it or write to it. So if we put out to the user, that supports the function associated with a read. Go back over here. We look at our device open. We're printing something here. We're going to tell our module, we're going to get this particular module. We have set our pointer. Down here is where we put something out to the user, as opposed to get something from the user if we were writing to it. We see down here in our write, you can call the write function. It's just going to say, sorry, we didn't write this. So I have nothing to read from you. We could use this for communicating between two people, kind of like a walkie-talkie, right? You know, you could have one person write to it and another person read from it, and you just keep going back and forth, and you can send messages back and forth. Okay. So back to this. So install the module, add the special node. Now we can read and write from it. Actually, I'll put all of this under this. Then we'll say uninstall. The module. We remove the module. We remove the special node in /dev/ whatever we called it. So you have to like fully uninstall it, so to speak. So that thing that's in /dev, that's the actual character device, but that's our way of attaching it to the major character device that the operating system provided us. And we'll see that here in a second, how that works. We'll come over here. Now I've written a couple of, this was the first character driver, right? All right, so I've written a couple of things in here. First, let's just look at our make file. So our make file, pretty much the same thing we had for other modules. The name of my file is chardriver.c. So my object file is going to be chardriver.o. I do my normal make using libmodules like we did before. Nothing's changed here. I basically copied this make file over and just changed the name of this guy right here. All right, now for install driver, I created a little script. So I just said vi install driver, or you can do it with VS Code if you want. Just create a file. And inside this file, what I did is I put in the commands to install it, show me what the node was, and then ultimately create the new device. The idea of me doing this is kind of like proof that it installed. Realistically, I was expecting that I would have to manually issue this, but I mentioned to you that I keep getting the same major number. The OS keeps handing me the same major number, which makes me think that, oh, I registered it once. It knows this thing's called chardev. Maybe I'd get a different one if I change the name of it. We can actually experiment with that in a second. But it keeps handing me a 242. So rather than making you copy it, because it is in this message will show it to you. Why? Because inside of our inside of our read. No, it wasn't the open. Where was it? Oh, no, it was in the initializing the module. That's when I said, hey, this is the command you need to issue to create that special directory. This is what will get dumped to that D message. All right. So in my script here that I wrote, which is just a file with some lines of commands in it, I intended to say, hey, let's just dump D message so you can see it. But then, so my intention was that you would then have to copy from that and run the command, but it kept being the same number. So I just put the command in there. So this will create it for you. All right. So what I did is I just created 3 entries like this into this command. So now you have 2 ways of running this. You can either use the shell, so you can say bash install driver and run the file directly. I like to make it executable. That way when you type in ls, you see all your executable things in green. install drivers, a program, reads, a program, uninstalls, a program. And you do that using chmod 755. In this case, I would have said install driver. This says read, write, execute for the owner, read and execute for the group, read and execute for everybody else. So I'm setting the mode for that file. So if I change this to 555, or let's call it, let's do it 333. Actually, I'm gonna do it 733. Well, 7 vector, that's gonna be a bad one. Read and execute, so I need to do it 6. Yeah, that'll work. Oh. Oh. Well, I'm a little bit hesitant to do this, but well, whatever. So, so now if I do, notice now I do ls install drivers no longer in green. It's not an executable file. If I do ls-l, it'll show me kind of a more detailed version, a long version of this. And we look at the install driver here, and here are the permissions. This is only read and write for the owner, read and write for the group, read and write for everybody else. It's not executable. All right. The typical executable thing you would say is 755, which says, I'm the owner, give me full permissions. If I want to change the content of this file, I can, so I should get write privileges. Everybody else, they can read and write it, or read and execute it. So chmod 755 is the typical go-to move for that. Now you notice it's back in green, and you would run it by saying /install driver. All right, it's going to ask me for my username or my password because I'm running it as super user. So it installed it. It then did the tail on the dmessage, but it also did the make nod thing. Notice it was 242 again. So the output of this guy showed me this is the command you should issue. Now, if I do an ls/dev ch star, it messes, so I need to do 242. This is it down here. This is the special file that's related to /dev/chardev, this 242. Right, so I created a special node in here that links to that. Let's see. I do cat/dev. Notice when I go like this, it shows me there's a thing in there called chardev. But that actually maps to, this is a unique device ID. The major device ID for this guy is 242. So if I say I want to talk to /dev/chardev, and I do ls/dev, here's all the stuff that's in ls/dev. Oh, it is in there. Why isn't it showing up when I search for, yeah, here it is right here. So that's the node that got created. All right, so the D message told you what you have to type in, but I put it inside of my install driver, this last thing. Sudo, make node, whatever. Okay, so that creates the character device link to the actual device that's behind the scenes, the character device, so that we could potentially read and write from it. Now, if I want to read from it, So read, I mean, one thing you could do, I could use VI to open it. Actually, that would be interesting to do because it won't let me edit it. /dev/chardev. Isn't that where it was? Oh, lowercase. Yeah, see, since it's not an actual file, it's that special node, I can't edit the thing. But if I say cat says, take the contents of the file and write it out. Or I could also say more, take the contents of the file and write it out one screen at a time, something like that. So if I look in our read file, all this guy is doing is calling cat/dev/chardev. So if I go ahead and do a ./read, it says I told you 0 times. The static count was 0 the first time. Static count is 1. Static count is 2, so on and so forth. Okay. Uninstalling. Oh. So in this, I'm going to remove the module, just like we removed modules before. Nothing new with that. And then I'm going to go in and I'm going to remove that character device. So clean everything up. Right? So the reality here is I've created these convenience functions. They're similar to makefiles in that, hey, this is something I need to do multiple times. And if you're not sitting there for 12 hours a day writing this stuff, you might forget it. You know, the command you have to type in, you have to go back. Or typically what I would do is I would do like a history grep for insmod or something like that. And this would show me my more recent insmod stuff. You know, we see some of the stuff when we were looking at command line arguments. Here's the ones from the more recent thing. So, oh, that'll work. But if I reboot my machine or my history file gets deleted for some reason, or it's been a long time and the history file has just cycled through and now we're on the new history, or I can't scroll back far enough, probably don't want to rely on the history file for everything, but it does work. Okay. So if I want to uninstall it, uninstall. Now it's no longer in there. And if I do a dmessage pipe to tail, oh, I didn't give any input, didn't write anything new when I uninstalled it. Okay, so that is a working read from a character device. Kind of see the cadence, how that's all working. All right, so let's start thinking about the Proc file system. At least we'll get started talking about it. So first of all, I'll show you here. If I do a cd, well, I'll just do an ls/proc. So these are, now notice here we have a bunch of numbers here, right? In blue, a zillion numbers. If I type in the command top, this will show me the current running processes on the computer. And right now it's showing me the processes that are using the top amount of CPU time. So here's 2016, the Gnome Shell. This is the windowing environment for Ubuntu. It's using GNOME as the windowing environment. So 2016 is my, seemingly it's in competition with a couple other things. Here's Visual Studio Code is up there, the terminal's up there. But these are programs we recognize, right? So 2016 is the program for Gnome Shell. So if I do an ls/proc grep 20, I'll just do star. Ooh, 201 star. Here's your 2016 up top here. So one of the files inside of /proc is in existence because it relates to a process ID of a program that's currently running in the on the operating system. So Proc/Proc stands for process. So the stuff that's in there, you'll have an entry in the /proc file system for every running process on the computer. Okay, which means that you have a unique way potentially for talking directly to a process, as opposed to having to talk to a process through a character device. Because what we're talking about right now is very basically different ways of communicating between programs, different ways of communicating through processes, different ways for a user to communicate to a program. That's what we've been faking, right? We've been reading from this file. So that's our way of digesting the output of a program, is by whenever we want something to happen, rather than run the program another time, the program's just there ready for us. So, the Dr. Locklear version of this might be to have this file just feed Chuck Norris jokes, something like that. Whenever you want a Chuck Norris joke, you just read from /dev/Chuck, and it gives you a Chuck Norris. We should write that probably. But, so that's one way the user might interact with that program, is through a module, okay? Another way is through the Proc file system. So I already started writing something here. Well, first of all, any questions on how I created these little helper things? Text file, put crap in there, and change the mode to be executable. So basically, once you get a command that works, copy that command, put it in the file, you don't have to worry about it anymore. Same thing like we put in the make file. So we type in make. The first couple times we had to screw with it to kind of get it working right. But once you have it working right, you want to make a change and rebuild your code. Poof, we got it. Go ahead. Sure. Yep, and cat is that program for concatenate. It takes the contents of, you could put 10 files after that if you want, and it concatenates them all together and dumps it to the screen. That's what cat does. Go ahead. No, it didn't. You saw the ALL from the uninstall. Yeah, no, it was, if I do var, it was uninstall, more uninstall. Yeah, so the ALL is from the end of the word install from that line. If I went into that file, that's all that's in there. Go ahead. VI is a command line text editor. It's the cool kids version of VS Code. Because I'm not that great at using VS Code. It is kind of funny. I move around the terminal way quicker than I can. This mouse stuff is all this newfangled junk. Go ahead. /dev. So there's already in the file system. If I just do a CD and I go to /, the / is like the root file system. It's like the C drive on Windows. So inside here, what we're looking at is effectively the POSIX standard, or POSIX-ish standard for Linux operating systems. And most more modern Unix operating systems all follow this POSIX standard. So you will always have a directory called bin. And inside the directory, bin stands for binaries. You're likely to find the binaries associated with the operating system. So if I go into bin and I press LS, here's stuff built into the operating system. If I want to kill a process, I can use the kill command. So for instance, if I say top and what was it? Where is code? Code's not using very much stuff right. I was going to kill code. Just cuz. Oh, there it is. 9812. Oh, it looks like I have two windows. So I can just do kill 9812. Is there another one? Killed off part of it. 9854. That was probably like a backup process that was like auto saving and stuff like that. Now I think it should be dead. Is this like a Hydra? You kill, you kill one head to grow back. Yeah, there we go. What you get. Fun with Linux. All right, so these are commands built into the system, probably operating system stuff. Some of them we might even be used to seeing. Oh, here's another one called Nano. Nano is the, how many of you have ever used Nano? A couple of you probably. Yeah, all of the, we try to be cool, modern Linux tutorial stuff typically use Nano because it's a friendlier text editor. You know, if I go back in here and I do Nano, my first, well, yeah, this is what Nano looks like. You know, so there's a, you know, assembly program. So Nano is a friendlier text editor than VI. VI was designed for touch typists, so you didn't actually have to take your hands off the keyboard. But VI, you have to learn the commands. So like to save a file, you do escape:WQ for write quit. That saves it and exits VI. And once you get used to doing it, you can do it really, really quickly. Nano was never actually a program in and of itself. In the early days of email, this is way before GUIs. The program that was commonly used for checking email, anybody know the program that was used for checking email? No, Vim is like a more modern VI. It's still for cool kids, but not as cool as original VI. Vim, what it does is it takes away, like if you're in normal VI and you use the arrow keys, you get weird symbols, right? Vim does away with that. It says, look, I kind of know what you mean, right? No, but there was a program that you actually use your email client, the equivalent of, you know, whatever, like equivalent of Gmail or if you have like I use Mail on the Mac, Outlook. The equivalent of that was a program called Pine. Okay, Pine, P-I-N-E. And it was all text-based. Embedded in Pine, and this is back in the days when most people used VI as their editor. Embedded in Pine was a text editor codenamed Pico. People liked Pico because they sucked too much to use VI. So what happened is they pulled Pico out and released it as its own editor. Well, they pulled the text editor out of Pine, released it as its own text editor called Pico. And then later on, they renamed that Nano. That's what Nano is. It's the text editor that was found in the email client called Pine. Don't use it, people will laugh. Is Pico on here? Yeah, there's Pico. Oh, it just calls Nano. Oh, man. This is like a history lesson. We're like looking at stuff from the 80s here. Actually, no, Pine was still a thing in maybe 93, 92, 91. Yeah. What was I saying? Oh, anyways, so if you're in the root directory here, so inside bin, you're going to see stuff that's operating system stuff. You also have a folder here called local. Oh, it's user local. So if I go into the user directory, here's user local. These are typically things installed in user space. Now, these are just folders. You can put anything in here you want. Okay, but generally speaking, if you were to get, you know, download a program and run through its installer or whatever, and it's like a game, it's probably going to put that in user local bin, or I see something here called user local games. That's probably actually an Ubuntu thing, the games folder. I'm guessing Ubuntu comes pre-installed with some games and crap, and that's where they put them. But maybe utilities, if I go into CD bin here, yeah, here's some tools that, oh, there's Yelp. Is that Yelp Yelp, or is that another Yelp? That's what it opens. So it's like it's Yelp for Ubuntu. It's just stupid. Yeah, whatever. So these would be more user things. Here's a assembler, NASM. It's kind of a common assembler, but it's installed in user space, not kernel space. So on and so forth. SBin is typically stuff that need to be run as super user. That's what goes in SBin. You still have a CD-ROM folder because that used to be a thing. That's where your CD, that was not just any device, that was an important device. It had its own folder reserved for it. Boot folder is where your, this guy probably uses Ubuntu. Bootloader doesn't use Grub, maybe? Yep, Grub. So this is like the thing that hands off from the BIOS to the actual operating system to get the thing launching. Stuff like that. Here's the actual Linux kernel. It's the compiled Linux kernel that's in here. This is whatever is the highest number, 135. Yeah. So this is the current version of it. Somewhere there was an update. This is the previous version. This is probably what originally got installed, was the 132. Mount directory, that's if you have network file systems or like a USB stick, that kind of stuff would show up in the mount directory. Actually, maybe media would map on here. Yeah, so media has, this might be a Parallels thing specifically. How Parallels maps my Mac side of devices and stuff over to this, which is going to be more of a my virtual machine I use as Parallels. Okay, so there, quick tour of Linux, I guess. But for us, the next thing we're looking at is this thing called the Proc file system. What are we doing on time? Okay, I got another minute or two. Is the Proc file system. And this is where we have files associated with running processes. And if you happen to want to see the running processes, you can do the top thing. You can also do, what is it, a ps.ax. This will show you all the processes. I think just ps will show you the processes. So this shows the foreground processes, which is the bash shell and then the process, the thing I just ran. ps-a will show me all the processes running. ps-ax will show me more information about what each of those processes is. If I want to know more about this, I can say ps-h, probably -h, it might be -help. Nope, -help. And this shows me the various things I can send to PS to make it work. If I want more depth, I can say man PS. So hopefully you're seeing this was like the internet. This was Google before Google, right? You can ask the operating system to tell you about these programs, and people who wrote these programs used to write them this way because that's how people figured out how to use them. You couldn't just go in Google or, you know, whatever. All right, so in our proc file system, we're gonna have a file for each of our running processes. This is not a normal plain Jane file that you would really write or read from. This is a specialty file, kind of like what we dealt with in our dev folder today, that allows you to communicate with a process through something like this. So if we were to kind of say, what's the topic of this course? We say systems programming, but what does that really mean? Maybe one of the core components of systems programming is this idea of inter-process communication. How do I have multiple programs on my computer? We're already very used to having human beings talk to a computer. Usually we like doing it with the keyboard and the mouse, right? But now we're seeing that, oh, I can type a couple things and I'm talking to the program, right? But I'm going through this module system instead of the program prompting me for stuff. But what if you have multiple programs running that all need to talk to each other? Or you have 2 or 3 programs that are, like we saw a few minutes ago, that code, VS Code, is running like a couple of times. Okay, we probably have one, I mean, I'm just guessing here, but if I was architecting something like that, I probably have one process running in the background in its own thread, maybe doing some auto saving, maybe every 30 seconds or something like that. So the event of a crash, you don't lose too much stuff. Maybe there's another process for whatever your active tab is. It's possible. And then you have another process for like the full application that handles, you know, the drop downs, the file, the edit, those kinds of things. So you really have multiple things that are talking to each other. But if you imagine you go over and you click on one of your files over on the left, your intention is you want a tab to open. So that might need to go and talk to the current active tab, or maybe it just creates another process on a per tab basis, however they've architected it. But you can imagine that there are situations where one of the VS Code processes might need to communicate with another VS Code process to get it to do its bidding. That makes some sense? Maybe it tells it, hey, this is the file whose contents I need you to show on the screen. It somehow passes a string to it. That tab program goes down and reads from the file system that file, puts it up. Now he's in charge of letting you type and save and all that jazz. Okay, so let's cut it off there for now. So what we'll do next time is we're going to come back and I already have some code started for the Proc file system, and we'll walk through that like we did before. Over the weekend, depending on where we get, I might introduce something to have you write in a write function to the character device. So if you wanted to investigate that, that would maybe get you ahead of the game a little bit. I suspect that's what it'll be, because I'm guessing we won't get far enough to Proc to do something related to Proc. Make sense? But no homework for Friday, probably homework over the weekend. All right, questions, comments, concerns, bribes? All right, I will see everybody on Friday.